Okay, hi everyone. It's nice to have everyone here, and I'm very excited to introduce our invited speaker for today who doesn't need any introduction, Jan LeCun, and you all know he's the VP and Chief AI Scientist at Meta and Silver Professor at NYU. He was also the founding director of FAIR and of the NYU Center for Data Science. And he has made significant impact to AI with his work on convolutional neural networks and impact on deep learning. And with that, he won the ACM Turing Award and also is a member of the National Academy of Sciences, National Academy of Engineering, and the French Academy of Sciences. So with that, I give you what you've been waiting for, Jan LeCun.
Thank you so much. Thank you to the organizing committee for inviting me. A real pleasure to be here. Okay, I'm going to talk about objective-driven AI, and this is more of a vision for the future rather than a list of results, and certainly not a finished system. This is a kind of presentation about the challenge of AI for the next few years. Okay, let's start with the obvious. Machine learning really sucks. I'm sure there's a bunch of people, old-timers here in the audience, who would be very happy of me saying this, but what I'm saying, the reason I'm saying this is because it's really bad compared to what we observe in the learning abilities of humans and animals. And you know, animals and humans can learn new tasks really quickly. They have common sense. They understand how the world works. The behavior is driven by objectives. And this is not the case for any AI systems that we have today, at least big ones. And we might ask the question, you know, is it a good pursuit? Is it a worthy pursuit to try to build machines that have, let's say, human-level AI? And the answer is yes. First, there is a scientific question of, you know, trying to figure out what human intelligence is all about, and the best way to figure this out is to build one that is similar. There's a technological question also, you know, can we do it? But then there is also a sort of product need for it. It's a good idea to basically build machines that are as smart or smarter than we are, because they will be augmenting our intelligence. They will be amplifying our intelligence. And intelligence is kind of the commodity that is most in need, perhaps, in the world. And there is a future in which will be all of our interactions with the digital world will be mediated by AI assistants. Those AI assistants will need to have human-level intelligence if we want them to not be frustrating to talk to, among other things. So it's a worthy pursuit. But we're nowhere near this, despite what we might read everywhere. And you're probably the best community to understand that we are nowhere near this, because most of us, like me, are in the trenches trying to make machines more intelligent. So when we hear people saying, you know, edge AI is just around the corner, we're the most skeptical about this because we see the obstacles. And one reason is that we're nowhere near edge AI is, you know, where are our self-driving cars? Driving is a task that any 17-year-old can learn in about 20 hours of practice, and we still don't have self-driving cars. And we have hundreds of thousands of hours of training data, and we have all kinds of sensors and stuff like that, right? Any 10-year-old can learn to clear out the dinner table and fill up the dishwasher in one shot, in a few minutes. So we can do this with robots, and it's not because we can't build robots, it's because we can't make them smart enough. So we're missing something big, obviously. And you know, things like machines that can figure out how the world works and have common sense and can do reasoning and planning. So that's what we need. That's the requirement for what I call advanced machine learning. I don't like the phrase AGI, artificial general intelligence, because I don't believe that human intelligence is general at all. Human intelligence is extremely specialized. And so AGI is complete nonsense as a phrase. But unfortunately, that ship has sailed. But anyway, I prefer the phrase advanced machine intelligence, and it sounds good in French because it means ami, that means friend. So we're in a English-French speaking country after all. So we need systems that understand the world, which means have mental models of the world that can be manipulated, have some notion of intuitive physics and things like this. We need systems that have persistent memory, other than just sticking stuff in their prompt. We need systems that can plan actions, possibly hierarchically, to fulfill an objective, and systems that are controllable and safe with guardrails. So that's the idea of object-driven AI. But before I talk about this, let me mention a little bit about self-supervised learning, because this is really, that has taken over the world of machine learning, but also it's an essential component of what I'm going to be describing. So the current most popular model of self-supervised learning is one in which you take a piece of data, let's say a piece of text, or possibly something else. You corrupt it, or you transform it in some way. In this case here, on this example, the corruption is to remove some of the words, right? So this is how we train LLMs and all NLP systems since 2017 or so. So take a piece of data, corrupt it. The original piece of data, call it Y, the corrupted version, call it X, and then train some gigantic neural net to basically fill in the blanks, figure out what's missing. In the process of doing so, the system will learn a representation of the text in this case that captures a lot of the dependencies between words and the internal structure of language. And that internal representation can be used as input to a subsequent task that may be supervised, for example, translation, hate speech detection, whatever you want to do with it, or question answering for that matter. Okay, so that's the idea of the denoising autoencoder or masked autoencoder. It's a particular type of self-supervised learning. And the idea of denoising autoencoder goes back many years. And of course, you can, there's a special case of this where, the neural net is built in such a way that it can only look at words that precede a particular word that it's trying to predict. And with this, you can build autoregressive large language models, which I'm sure many of you are very familiar with, right? So you train a system to predict the next word following a sequence of words, and then you can inject that word into the input, and now that becomes part of the input, you can predict the second word, shift that into the input, the third word, etc. That's autoregressive prediction. Of course, nothing new there. Autoregressive models have been around for a long time, but what's different today is, of course, the size of that system and the fact that you can only make predictions that are approximate, so you have to represent the uncertainty in the prediction, but the typical size of a vocabulary for such model, the number of different tokens, which are subword units, is somewhere between 30,000 and 300,000 or something like that. So we can represent the uncertainty by a big vector of numbers between 0 and 1 that sum to 1 that represent the distribution, the predicted distribution. So we can handle uncertainty in domains like this that are discrete. So those systems, autoregressive LLMs, as they should be called, are amazing in terms of their performance. I mean, the fact that they work at all is really amazing. But they do make stupid mistakes, factual mistakes, hallucination, inconsistencies, they have limited reasoning and planning abilities. They don't really understand the physical world, even if we augment them with vision. They certainly have very little common sense, and no persistent memory other than whatever they inject in their own prompt. So the lack of planning is a huge problem. So some of the models that have been made available are open source, and some of them are purely closed source. I think the open source ones are very interesting for this community because that's what we can do research with, and also actually build products from them. And of course, I'm sure a lot of you are aware of the Llama family of LLMs from Meta, which you can download at this address. And you can use in various cloud services and how they work. You know, you type a prompt and it tells you something about it. This is a picture I took in my backyard in New Jersey, by the way. This is the Messier 51 pair of galaxies. And you know, you can fine-tune them for like having various personalities or different expertise. So Meta has been kind of playing with this, and you can access different personality LLMs through Facebook pages or Messenger or WhatsApp. And you know, with self-supervised learning, you can also do things like train LLMs that are multilingual. So this is an example of a recent system called Seamless M4T from my colleagues at Meta. They can do translation and speech recognition and text-to-speech and speech-to-text in 100 languages as the input and 35 languages on the output. So you can do text-to-text, text-to-speech, speech-to-text, and speech-to-speech. And the speech-to-speech is particularly interesting because, in principle, you can use such systems to do translation, speech-to-speech translation for languages that do not have writing systems, non-written languages. Okay, so SSL has been an enormous boon for machine learning and AI more generally. But this idea of autoregressive prediction really has major flaws. The first flaw is that if you assume that there is a certain probability for that, such that every token that is produced takes you outside of the set of proper answers, then the probability of staying within the set of proper answers decreases exponentially with the length of the text that is produced. Now, of course, the errors are not independent, so it's not really like that. But in principle, it's kind of an intrinsic flaw, if you want, of autoregressive prediction. This would be fixed by systems that are capable of planning, right? And most of us plan or answer when we have a dialogue with someone. We plan or answer before speaking it or writing it. And we don't plan it in the language that we're speaking. We plan it in sort of at the abstract level. All of us here who know multiple languages, we don't formulate our thoughts in any particular language, but you know, in some sort of abstract internal format, if you want, and then we turn it into language, and that's the autoregressive part, perhaps. So it would be only logical that LLMs work the same way, that it would elaborate an idea, an abstract idea, and then turn it into words as a second step. It's a bunch of papers that have been published, including by Rao, who's sitting right here, but also by cognitive scientists, including the MIT team, that tend to show that LLMs have very limited capabilities for reasoning and planning. In fact, Rao taught a tutorial earlier this week about the planning ability or non-ability of LLMs. A few months ago, I wrote an article with a colleague of mine, Jake Browning, who is a philosopher. This is an article in a philosophy magazine, actually. But he's the card-carrying philosopher, I'm not. And this is about the fact that if we try to build intelligent systems purely by training them purely from text, we are essentially eliminating a lot of what constitutes human intelligence. In fact, arguably, most of human intelligence has nothing to do with language. It has to do with our experience of the world, of the physical world. This is certainly true for most animals that don't have language. Let's say orangutan. Orangutans are almost as smart as humans, and they don't have language. So Autoregressive LLMs suck in addition to machine learning. They're good for writing assistants and stuff like that. We're fooled into thinking they are smart because they are fluent in language, but that is just another example of the Moravec paradox, that there are things that are simple for computers, hard for humans, and vice versa. So, as I said before, we're still far from human-level intelligence, and because of the limited planning abilities and understanding of the physical world of current LLMs. But there is no question in my mind that at some point in the future, probably not too far, probably in the lifetime of a lot of people in this room, we'll have systems that are as smart as humans in all the domains where humans are smarter, and potentially smarter in many domains. As I said before, humans' total intelligence will increase, and we should welcome this, not fear it. I'll come back to this later. So we're missing something really big. Again, we keep bumping against the Moravec paradox. How is it that very simple tasks that we take for granted, that we think are simple, actually turn out to be really complicated to reproduce in machines? Any physical act and planning, perception, we have a good handle on now, but action, not so much. And there is perhaps a reason for this. So if we try to quantify the amount of information that a typical LLM is trained on, so typically that would be something like 10 trillion tokens, and a token is typically 2 bytes, okay? So the amount of training data for a typical LLM nowadays would be 10 to the 13th bytes, which sounds a lot. And it is a lot. It would take 170,000 years for most of us to read through this, reading 8 hours per day. So it's an enormous amount of data to digest in text form. But text is very low bandwidth. The higher bandwidth modality that humans, or sensory input that humans have, is vision. And you can talk to developmental psychologists. You'll hear from Liz Spelke after me. She knows way more about this than I do, but I got those numbers from your dear colleague, Linda Smith. So a 4-year-old child has been awake 16,000 hours, which, by the way, is only 30 minutes of YouTube uploads, so it's not that much data. We have 2 million optical nerve fibers going from our eyes to the visual cortex. Each fiber carries about 10 bytes per second, something like that, probably a bit less, but doesn't matter. And so the overall data volume that a 4-year-old has seen is 10 to the 15 bytes. That's 50 times more than the amount of data that we train our biggest LLMs on. So a 4-year-old child has seen 50 times more data than the biggest LLMs. In 300 hours, a child has seen more data than an LLM, than the biggest LLM that constitute, trained on the entire publicly available text on the internet. So, obviously, we're not going to get to human intelligence without some sort of sensory data, because there's way, way more information in sensory data, particularly in vision, but also touch and other modalities. And this is what most human intelligence is about, and certainly all of animal intelligence. Okay, so how to take advantage of this? Perhaps with something called objective-driven AI. And I wrote sort of a vision paper about this about 1.5 years ago. And there's various versions of this talk that you can watch, emphasizing different aspects. So it's kind of a modular architecture composed of multiple subsystems. And rather than just sort of listing them all here, I'm going to tell you a typical episode. So I'm assuming the system is trained. Okay, and an episode is as follows. The system perceives the world. So that goes through a perception module that turns raw percept into a representation of the state of the world, at least the part that is currently perceived. That may be combined with the content of a memory, which has some idea of the rest of the state of the world that you're not currently perceiving. So the collection of the two is basically our current idea of how the world works, of the state of the world, sorry. And you feed this to a world model. The world model is really kind of the centerpiece of that entire architecture. The role of the world model is to predict what's going to happen next. What is going to happen, perhaps as a consequence of a sequence of actions that you're imagining taking. Okay, so the action sequence is the yellow blob at the bottom. You send the action sequence to the world model, and given the current state of the world and the action sequence, the world model predicts the final state of the world, the outcome, essentially. Now, this final state goes into a bunch of objective functions, one that measures whether a particular task has been achieved, and perhaps a bunch of others that are guardrails. So there are cost functions that measure to what extent the trajectory followed by the system or the sequence of actions is safe, regardless of what you mean by safe. Okay, so that system is objective-driven. Okay, so I should say the way the system operates now is that it tries to find an action sequence that minimizes those objectives according to its own world model. And if all of the modules there are differentiable, so both the objectives and the world model, you can essentially backpropagate gradient through the action, and by gradient descent or gradient-based method, optimization method, figure out the action sequence that will minimize the objective. There might be situations where there are sort of discrete choices to make, or the action is discrete, and so you might have to use other types of optimization methods, but basically it's an optimization method. So this is fundamentally different from propagating through a fixed number of layers and then outputting a token, which is not Turing complete. This is Turing complete. It's Turing complete because any problem can be formulated in terms of an optimization. So this sort of computational model, if you want, is universal in some way. You can formulate anything in terms of optimization. So it's intrinsically more powerful, if you want. It's very similar to the type of idea that people have been proposing in probabilistic inference in graphical models and factor graphs, where you have a bunch of variables you observe and a bunch of variables you don't observe, and you figure out the value or the distribution over the variables you don't observe by maximizing some likelihood or minimizing some negative likelihood. Same story here, except here, it's not necessarily a likelihood, it's just an objective. Now, generally, your world model, your action sequence has multiple steps, and your world model can be sort of unfolded in time to kind of take into account the various steps of actions. And so this is a very simple example here. When you have two actions, you run your world model twice so as to predict the final state after two steps. And the guardrail cost take into account the entire trajectory, not just the final state. And then you plan the action sequence to minimize the objectives. Now, this is extremely classical in optimal control and in AI generally. It's called model predictive control in optimal control, right? You have a model of the system you're trying to control, and then by gradient descent, essentially, or gradient-based method, you figure out a sequence of commands that will arrive at a particular result. NASA uses methods of this type to compute rocket trajectories to rendezvous with a space station or something like this, and has been doing this for 60 years at least. So this is not a new idea at all. The question is, how do you train the world model so that it's appropriate for any situation the system might encounter? In classical optimal control, the world model is written by hand. It's a set of equations, differential equations. You discretize, and there is no learning really. So there, the big question is going to be, how do we learn this world model? And again, this is not a new idea. There have been attempts at doing this going back to the 1980s. It's just now we can perhaps do it at scale because we have the computing resources and perhaps some new concepts for this. Now, generally, the real world is not particularly predictable entirely because we don't have perfect perception, and the world perhaps is intrinsically non-deterministic. So we need to have latent variables that essentially could be drawn from a distribution or swiped over a set that would essentially parameterize the set of possible predictions that the system might make. And that would complicate the planning, of course. This is planning under uncertainty now. And there's several strategies for this, planning with sort of defensive policies against bad things that can happen, or other techniques. So it makes everything more complicated, but still possible. But what we want to do eventually is hierarchical planning. So basically planning at multiple levels of abstraction. And we do this all the time. We may not realize it, but we do hierarchical planning all the time. For example, if you want to go from, let's say I'm sitting in my office at NYU and I want to go to Paris. I could try to do the planning of my entire trajectory from my office in New York to Paris in terms of millisecond by millisecond muscle control. But of course, that would be kind of crazy. Also impossible because I don't have all the information about how to do this planning. So what we do is we do hierarchical planning. To get to Paris, I first need to go to the airport and catch a plane. Okay, now I have a sub-goal, going to the airport. How do I go to the airport? It's New York City, so I go down on the street and hail a taxi. How do I go down in the street? That's another sub-goal. I go to the elevator, take the elevator down, work out on the street. How do I get to the elevator? I have to get up from my chair, open my door, get to the elevator, press the button. How do I get up from my chair? Well, I have to move my arms in a particular way and blah, 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 right? I mean, all of those require some planning, and it's all hierarchical down to the level where, I can take the first action that I, plan in terms of muscle control and actually do something. So we do hierarchical plannings. Animals do hierarchical plannings. We have absolutely no idea how to do this properly with AI systems. A lot of people have worked on hierarchical planning, and a lot of AI systems that plan actually do it hierarchically, but they're designed by hand. It's a little bit like computer vision, pre-deep learning, where you would design the feature level and then train a classifier on top. Here's the same thing. When AI systems do hierarchical planning, the intermediate representation of how you do planning and the actual planning algorithms are hardwired. They're handcrafted. So the big question here is, how do you learn this? How does your cat learn to plan? You've seen cats like wanting to jump on a piece of furniture, and they sit at the bottom and they move their head, right? And then they go jump, bounce, 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 and they're on top of the furniture, and you can figure out how they did it, but that's a lot of really smart planning that they've been doing, and hierarchical planning. So that's a huge, if you're looking for a good topic of PhD, and you have 5 years, in front of you, how to learn hierarchical planning is a good topic. If you have some friend that has figured out how to learn world models, because you need hierarchical world models for that. Okay, so how can machines learn world models from sensory inputs? With self-supervised learning, obviously. So this is not going to work with reinforcement learning or supervised learning because it's just not enough data. And so one question we might ask ourselves is, when do babies learn basic things about how the world works? And there can be some discussions. I see Lee's going like, no, object permanence, that's hardwired. Maybe not. I don't know. In any case, it happens really, really early, in the first 2 months or something. But it takes quite a while for babies to learn things like gravity and intuitive physics. I think the estimates vary between 6 months and 9 months. I got the 9 months here. I'm not sure if you agree with that estimate, but if you show the scenario at the bottom here to a 5-month-old, 6-month-old baby where a little car is on the platform and you push it off the platform, it appears to float in the air. A 6-month-old baby would probably not be particularly surprised and not pay attention. A 10-month-old baby would go like the little girl here at the bottom, be extremely surprised because she has learned in the meantime that objects that are not supported are supposed to fall. So, how do babies learn those basic concepts? Mostly just by observation. There's, of course, interaction, particularly after 4 or 5 months. But before that, it's mostly just observation. Now, of course, you could say, well, let's use the architecture that we use for text, right? Take a video, like train a system to predict what's going to happen in a video, and perhaps it will understand the underlying structure of the world, because it has to if it wants to be able to predict what's going to happen, right? So take a piece of video, mask a chunk of it, let's say the second half of it, and then train some gigantic neural net to reconstruct what's missing in the video. And perhaps you have some information about the transformation that happens between those two steps, or maybe the action that the characters in the video have been taking. That's the A variable, or perhaps not. We've been working on this at FAIR on models of this type since 2014, so pretty much 10 years ago. And basically been a complete failure. And the reason is, it's very difficult to predict exactly what's going to happen in a video. There is a lot of uncertainty about it. So if you train a neural net to predict what happens in the video, you get this kind of prediction that you see at the top, where the predictions are very blurry. The first 4 frames of that system, of that video, are observed, and the last 2 are predicted, and they get extremely blurry. The second column from the left, the bottom animation, is also a prediction from a large neural net trained on videos, and you also get blurry prediction. Why are the predictions blurry? It's because there are many plausible things that can happen in the world, and the best thing a system trained to predict what's going to happen next can do is predict the average of all the plausible futures, and that's a blurry video. So we try to fix this with all kinds of stuff, with GANs, with different techniques, and basically nothing works. So about 4 years ago, some of us had a bit of an epiphany. Perhaps the solution is to not use generative architectures that try to reconstruct pixels, but to do something else. And that something else is joint embedding, particularly an architecture called JEPA, Joint Embedding Predictive Architecture. So what is a JEPA? It's something like this. So here, instead of attempting to reconstruct Y, you run Y through an encoder, and then you train the system to reconstruct the representation of Y after the encoding. This is a much easier problem to solve because the encoder might eliminate all kinds of details about what goes on in the world that are very, very hard to predict. If I take a video of this room, I start by pointing it in this direction, and then I pan in that direction. A good video prediction system will probably predict that there is a room, and there's going to be another corner in the room, and the panels on the side are probably going to be the same color, and there's going to be people sitting in chairs with a pretty much uniform density, but it cannot possibly predict the precise texture of the wall in the background, the positions of all the lights, and certainly what every one of you looks like. It's impossible to predict, right? Information is just not there. And so what if we made predictions in an abstract representation space where all of those details were eliminated, and now the prediction problem became much simpler? So that's the idea of JEPA, Joint Embedding Predictive Architecture. Why joint embedding? Because you're embedding both Y and X, and then you're making prediction in the representation space. Okay, so that's really the more general version of self-supervised learning. Take X and Y, embed X, embed Y. X is a transformed or corrupted version of Y, perhaps through an action or some variable that you might observe that indicates what goes on to some extent. Embed both of them, and then and train a predictor to predict the representation of Y from the representation of X. Okay, so basically filling in the blanks, but in representation space. Right? So on the left, you have a generative architecture. On the right, you have one of those joint embedding predictive architectures. You could think of the generative one as being a special case of the joint embedding one, where the encoder for Y is the identity, right? That makes the problem fiendishly complicated. So how are we going to train those JEPA architectures. And you can augment the architecture with latent variables to indicate that the prediction may not be deterministic. You may have objective functions that are used to train the system to kind of drive it to learn interesting features as opposed to irrelevant ones. This is represented by this C cost function. But before I explain exactly how we can train this, I have to explain the concept of energy-based models. So an energy-based model is basically a weakened form of probabilistic modeling which we cannot apply to those JEPA architectures. And really, energy-based model is a very sort of general framework that allows us to really understand what learning can do. And the idea is to capture the dependency between variables through an energy function. How does that work? So if you have a neural net deterministic function that maps x to y, you can only have one y for any given x, right? Because it's a function. So if you want multiple y's that are compatible with an x, which is really what we're looking for here, because there are multiple futures that are plausible given an observed past and present, then you have to use what's called an implicit function. So basically, a function that tells you whether a particular y is compatible with the x that you're observing or not. Okay, so it's a function of x and y that will have a scalar output, which is not represented here. Whenever I draw a square, that's a cost function, and the output is scalar and implicit. So you feed it an x and a y, and it tells you 0 or a small value if y is compatible with x. For example, if y is good continuation for the video x, or a large number if y is not a good continuation or a sort of compatible value with x. So imagine the situation here on the right where x and y are both scalar variables, and your data set is those black spheres. So you want to give low energy in regions around the data points and then higher energy to the rest. So the learning problem is going to be to shape that energy function. The energy is not a loss function used for training. It's an energy function used for inference. Okay? And the learning is going to shape that energy function by changing the parameters of some neural net so that it takes low energy on the data set, on the data points, and then higher energy everywhere else. Now, to do this, there are two types of methods, two families of methods. Contrastive methods. So contrastive methods consist in changing the parameters of the neural net that computes the energy in such a way that the energy of the data points goes down. So you show a training sample and you tweak the parameters so that the energy goes down. Easy, you can do this with backprop. And then you generate other samples, those flashing green dots, and you do the opposite. You make their energy go up. Okay, so the green dots have to be outside of the manifold of data. And by pushing down on the data and pushing up on things outside the data, maybe the energy will take the right shape. You can formulate this in terms of a loss function that depends on positive samples and negative samples. That's why it's called contrastive methods. Okay, there's a wide variety of contrastive methods, but that's kind of the general idea. If you don't have those green points, you run the risk of a collapse where the energy function basically is flat everywhere, and as a consequence does not capture the dependencies between the variables in your system. Now, there's another set of methods that I actually prefer now, even though I kind of invented the contrastive methods in the 90s, and it's regularized method. And there the idea is you have some sort of regularization term in your system that penalizes you for making the volume of space that has low energy too large. Okay, so it tries to shrink as much as possible the volume of space that has low energy. All right, so those two different methods, contrastive and regularized or non-contrastive. I prefer the non-contrastive because I think they scale better in high dimension. But there are theoretical papers, including from my group at Meta, that show that there's some sort of duality between those two sets of methods. Okay, so I'm making a bunch of recommendations. Abandon generative models. Okay, this is the most popular thing that everybody's talking about. If you're really interested in human-level AI, systems that understand the world, forget about generative models. right? Use those joint embedding. Abandon probabilistic modeling. Use energy-based models, okay? A theoretical pillar of machine learning. Abandon contrastive method in favor of those regularized methods. Again, very popular at the moment. And of course, as I've said for 8 years now, abandon reinforcement learning, or at least minimize its use because it's so inefficient. Okay, so how are we going to train those JEPA architectures? Particularly, how are we going to train them to prevent this collapse? What kind of regularizer are we going to use to prevent collapse? So here's an example of a technique, and there is half a dozen different techniques for doing this. I like this one. It's called VicReg. Well, this is really information maximization. So the basic idea of this is to prevent collapse, is to make sure the information content coming out of the encoder is as large as possible, okay? And at the same time, the predictor is trained to reduce the prediction error in representation space. So the system basically has two competing objectives. One is carry as much information about the input as possible into the representation. And the second one is minimize the prediction error in the representation space. So if the system carries too much information, it's not going to be predictable, and your prediction error is going to be large, right? On the other hand, if the system does not carry enough information into the representation, prediction is going to be super simple, but then your system is not going to learn anything useful. And in fact, that's a collapse. So the collapse is a situation where the system basically ignores the inputs, produces constant representation Sx and Sy, and now the prediction problem becomes trivial. And so if you measure the energy as being this prediction error of the predicted Sy and the Sy, you get zero everywhere. You get a flat energy surface in the entire space. It's not good. So one way to fix this with regularization is to have a way of estimating the information content of Sx and Sy and try to maximize that, okay? Hence the minus sign in front of information here. If you have a latent variable, you also need to minimize the information content of the latent variable, but I'm not going to go there. Okay, so one method for doing this is VicReg, and it's a bit of a hack, because if we want to maximize the information content contained in a vector, we really don't have any good ways of doing it. And the reason is we do not have lower bounds on the information content, we only have upper bounds. So we're going to compute an upper bound on the information content, and we're going to push it up. And we're going to cross our fingers, hoping that the actual information content will go up with it. And it kind of works, but it's a hack. Okay, so how do we prevent the collapse? How do we maximize the information coming out of the encoder? First thing is, we want to make sure that each variable of the vectors coming out of the encoder doesn't have zero variance, basically changes, right? So what we're going to do is compute the variance or standard deviation of each variable over a batch of samples, and then have a loss function during training that is going to try to make the standard deviation larger than 1. We can use a hinge loss for that. Okay, so that's what's written here. But then the system can still cheat. It can make all the variables equal or linearly dependent of each other. So still the information content would be very low, despite the fact that the standard deviation is above 1. So to prevent this from happening, we also minimize the coefficients of the covariance matrix of those variables so that they're close to 0, right? So compute the covariance of two variables coming out of the encoder over a batch, let's say, and make sure that those two vectors of activities for a pair of variables over the batch are orthogonal. That's what setting the off-diagonal covariance matrix term means. So now we have variables that are not collapsed and are uncorrelated. There are other techniques actually that are very similar to this, one by Yima's group at Berkeley called NCR squared, that he came up with more or less independently from us. Okay, and that's still not enough, because you can still have nonlinear dependencies between the variables. So the trick we play here is that we take the Sx vector and we run it through a neural net that basically extends the dimension, typically by a factor of 2 or 4. And then we do the covariance matrix trick of trying to make the covariance matrix as close to the identity as possible. And that has the effect of making the original variable of Sx more independent of each other. Not completely independent, but more independent. So that's the VICREG technique, variance invariance covariance regularization. And it works really well. We have some proof that this expander technique actually makes things more independent if it's nonlinear. And then we can use the representations learned by those systems as input to a subsequent downstream supervised task and measure performance, freezing the network and just training a head on top of it. And this gives decent performance on things like ImageNet and various other data sets like Places, Pascal VOC, INAT, COCO, etc. for detection. I'm not going to bore you by going through the details of this table, but essentially this technique kind of works just as well as other SSL methods, maybe a little better, and doesn't have some of the constraints that other methods have. In particular, the two encoders don't need to share weights between them, so you can use them for multimodal training. We have an updated version of this that is designed to handle local features so that you can use this to train an object detector and segmentation system, and we get improved performance on segmentation and detection. There's another family of method which I would call distillation methods. So there, the collapse prevention, the way the collapse is prevented is not entirely clear. But the basic idea here is that the two encoders have to be identical, and you make them share the same weights, except that the encoder of Y gets a version of the weights of the encoder for X, which is sort of a time average, exponential moving average of the weights, past weights of the encoder for X. Why is this a good idea? We don't know. Why does it work? We don't know. Why does it prevent collapse? We don't know. Or at least I don't understand why. There's a whole bunch of papers that have been written on this. I'm not convinced by any of them, basically. And the red cross indicates that you don't backpropagate gradient through the encoder for Y. You only backpropagate through the encoder for X. So you could think of the one on the right as being a teacher and the one on the left as being a student. And basically, you train the student to predict the representation that is produced by the teacher. So there's a number of methods for this, BYOL from DeepMind, SimCian, DynoV2 from Meta, and it works really well. This is examples of DynoV2. So if you want a completely self-contained, pre-trained, generic vision feature extractor, just use DynoV2. As of today, this is the best we have. It's not because the method is the best, it's because it's the method that has been trained on the largest data set, and so you get the best features. It's being really kind of tuned properly. You can just download it from this address. And it gives really good performance when you train ahead on top of it for any kind of task you want, either generate feature extraction, object classification, segmentation, including for video, depth estimation. So these are heads that have been trained on top of DynoV2 to do depth estimation and segmentation, and it works really well. We have applications of this in biological images, and in this case, environmental data, where using DynoV2 features and then training on a small amount of data that indicates the height of the canopy from satellite images, we can actually estimate the height of the tree canopy everywhere on Earth, and then have an estimate of how much carbon is captured in vegetation, essentially, which is an interesting thing to have. So a new type of distillation method is called IJEPA. This is a paper from last year, early last year. And again, it has this idea of taking an image, corrupting it by masking it, indicating which parts are masked. So this is the A variable I was indicating in the previous JEPA architecture, and then training the encoder and the predictor to predict the representation of the image, the full image, given to the encoder at the bottom. Again, there is this exponential moving average weight sharing. And this method is really fast to train, gives excellent results. This is the best we have, actually. it's not as good as Dino as a generic feature extractor because we haven't trained it on the same large data sets, but it's really good. In particular, it works better than MAE, which means masked autoencoder. So masked autoencoder is a technique also developed at FAIR for basically training a vision system in self-supervised manner as a denoising autoencoder by taking an image, masking a whole bunch of it, and then training a system to reconstruct the missing parts. And so here this compares with reconstructing images, basically a generative architecture versus using this joint embedding architecture, the JEPA. JEPA seems more efficient. Again, a lot of good results there, which I'm not going to go to in detail, but on ImageNet with a tiny number of training samples, and this is ImageNet with only 1% training samples for supervised. More recently, we used the same idea for a paper that just came out last week called Video JEPA, and it's open source. There's a blog post and there's a paper. That system basically is what I showed you earlier, except the masking is not masking the future, but masking a whole tube within a video. So you take a video and you mask a whole bunch of regions for all times, okay? Typically a video here would be 16 frames. And then train a big neural net to predict the representation of the full video from the representation of the partial one. And again, this works really well to kind of pre-train a video classification system that can recognize actions in video. This chart represents the performance, the accuracy for 2 video dataset. The x-axis is for a video dataset that basically doesn't have much motion in it. I mean, you can recognize the action by just looking at a single frame. And the vertical one is one in which you have to watch the whole video to figure out what's going on. And so VJEPA really works well for this second type of video, and it doesn't require any prior knowledge, really, no data augmentation of any particular type except masking. And it can be trained from video, like Dino, for example. It doesn't use text like OpenClip needs to do. And it can really, with only a few examples, basically recognize actions in video. So the representations that are learned for video are pretty good. I'm going to skip some of the details of the results. And again, it's very cheap compared to other methods. Skip some reconstruction and then come to the conclusion. So there's a number of problems that we have to solve if you want to make progress. Basically use those JEPA architectures, not just to learn features for video, but to train them as world models. So things where the predictor will take an action and then tell us what's going to happen as a result of this action so that we can use this for planning. We've done some work on this in the past, and there's some interesting work from Daneja Hafner, for example, who is now at DeepMind when he was a student in Toronto, on using models of this type for planning. But there's no system I can point to that basically use world models of this type trained from natural data that allows us to do planning end-to-end. So training a JEPA with regularized latent variables, I think, is going to be a challenge. Using planning algorithms in the presence of uncertainty is going to be a challenge. We're going to have to learn the cost modules, where some of them we're going to be able to build by hand, just hardwire them, but some of the other cost modules, we're going to have to learn them. It's very much the same as what people call a reward model for an LLM, right? It's a thing that maps differentiably from the internal state representation, the representation of the state of the world, and maps that to a cost, okay? You might have an idea of the cost, but you might have to train a differentiable cost function to approximate that real cost. So planning with an accurate world model is a big issue that I worked on with one of my students a few years ago to kind of regularize the world model to not go into regions where it's inaccurate, but that may not be sufficient. And that's where we might need to use reinforcement learning to basically adjust the world model as we go. So with that, we might be able to build LLMs that can reason, plan, and are driven by objectives, not just LLMs, but also systems that can control robots. And the big challenge is going to be with hierarchical planning. We still don't know how to do that. The fact that those systems are controlled by objectives will make them safe and controllable, because we can put guardrails to make sure that they stay within limits. So if you have a robot that you ask to fetch you coffee, is going to have a guardrail that says, don't kill anyone on the way. So if someone stands in the way, don't run them over to get me coffee, right? So designing those guardrail objectives may be not simple, but certainly not impossible. And we're kind of familiar with the concept. And eventually we might have AI systems that will help us in our daily lives, will be as smart as we are, will augment human intelligence. Those platforms will have to be open source, because if they mediate all of our interactions with the digital world, we need them to be diverse. For the same reason, we need a press that is free and diverse to reflect multiple languages, cultures, value systems, political opinions, centers of interest. We also need AI platforms that are diverse. And the best way for them to be diverse is that there is a small number of open source platforms that anyone in the world can fine-tune for their own purpose. And anyone else in the world can have access to them and get the opinion, value system, culture, language that they want. Okay, so it's very important for the future that AI platform be open source, or at least available in open source. And it's important for democracy, basically. So be very careful of people who say AI is too dangerous to put it in the hands of everyone. You need to regulate it, and basically you would make open source illegal. I think it's extremely dangerous. But in the end, AI is going to augment human intelligence, and perhaps the effect on humanity would be similar to the effect of the printing press in the 15th century, where people got smarter all of a sudden because they had access to more knowledge. So maybe it's going to be the same thing. It's going to be a new renaissance, perhaps. And we're doing it. You are doing it. I'm too old. Thank you very much.
Thank you, Yan. So we only have time for one question, and then we have to move on to the next speaker. I would also suggest that at the end of the second speaker, both speakers can stay behind if there's additional questions afterwards. So let's just have one question. You're ahead, go.
Hi, Yan. So there's been this arms race for quite a while between adversarial examples and defenses against adversarial examples. Why do you think that won't happen with guardrails?
Okay, well, there's several types of adversarial examples, right? There is the type of adversarial example where you tweak an image a little bit, and the system, if it's an image recognition system, gives you a completely different category than the thing that humans would give. I think to some extent that's a bit inevitable, because the recognition functions are kind of one-to-many mapping, highly contractive. And so there's going to be, and they're trained on a tiny sliver of the input space. And so the behavior of those systems outside of the tiny sliver they've been trained on is unpredictable. I think if you have systems that are more JEPA-like, which basically reconstruct representations at various levels, that would, in my opinion, mitigate the problem, because it will allow the system to detect whether the percept is consistent or not.
Yeah, but I'm not talking about adversarial examples per se. I'm talking about the guardrails you're talking about.
Right.
Why wouldn't, China has 50 times more people than the FBI has on cybersecurity. And suppose they put all of those on attacking your guardrails.
Well, So the question is like, how robust can you make those guardrails to make them resist adversarial attacks? I think the first question is like just how you design those guardrails so that the system behaves properly, even if there is no adversarial attack. I think that's probably the first order of things. And some people have speculated that this may be very difficult because if a system is super intelligent, like how can you make sure that the guardrails you put in place are proper? I think we're familiar already with designing guardrails so that the behavior of people or super intelligent entities actually is aligned with humanity. That's called laws. And laws apply to people, but also to corporations, which basically are superhuman entities, right? So I think we're somewhat familiar with this concept of changing the objective function of an entity so that it behaves properly or semi-properly. That's the first point. The second point is with current LLM, autoregressive LLMs, the only way you can define the task is through the prompt. And the problem is there is no way that you can train a system with all possible prompts so that the behavior is guaranteed to be aligned with whatever it is that you want it to be aligned with. And so an autoregressive LLM does not have an objective and can be easily jailbroken by changing the prompt so that it escapes its training, essentially. Now, if you put the objectives must be optimized at runtime, at inference time, then the system cannot escape obeying those objectives. That's what makes it controllable and safe, basically. And so that's kind of the basic idea of that.
Well,
but yeah, there's a broader question.
let's thank the speaker again. And